All right, let's get on with our 10.3 here, infinite series. Now, the majority of this chapter is going to be based on series, and they're going to be infinite series. This first section, we are going to cover two types of infinite series. These two types, we're going to cover geometric and telescoping. These two types of series are the only ones that are going to have an actual value. So our first one here is geometric series. So of these first two, we're going to have geometric and telescoping. So of our geometric series, this is the criteria. This is what it can look like. So we're going to let A not equal 0 and R be real numbers. That means both A and R are real numbers, but A cannot equal 0. All right. Now here's the main criteria. If the absolute value of R is less than 1, then with this series here, when I go from 0 to infinity, because it's an infinite series, AR to the K is going to equal A over 1 minus R. That's going to happen. So the criteria of R has to be true in order for it to come up with this. If the absolute value of R is greater than or equal to 1, then the series diverges. So here's the moral of the story. You have this infinite series right here. An infinite series that I'm looking at to make this geometric is I have this R to this K. K is my variable. A and R are real numbers. So if I have to this variable that I'm looking at, if this R value is less than 1, then this is going to be the value of my series. If R is equivalent to 1, equals 1, or greater, then there's no work to be done. You just straight up say that this diverges and then you're finished. All right, so I'm going to write out, I think this part is helpful because sometimes this helps whenever you work through this. If I have this infinite series here, I'm going to scoot this up just a tad. My series of K is going from 0 to infinity of AR to the K. If I were to plug all of this in that I'm looking at, this is going to be AR to the 0 plus AR to the 1 plus AR squared plus R cubed, etc. Right? That's my infinite series. So whenever we said series, it's you're plugging in these values to the next one and you add those up because it is that that I'm adding as I go through all these different series, right? I just add it up. I plug in that value and I add to the next term, next term, next term. Okay. Now look what happens. If I'm plugging this in, then this ends up being A times R to the 0. Anything to that 0 power is just going to give me A, right? Because it'll be 1. A times 1 is just A. And then I have AR plus that AR squared, AR cubed, etc. Look at what's in common here. For all of these terms, I have an A in common. So if you factor out that A, you now have 1 plus R squared plus R cubed, etc., right? Okay. So if I want to find my actual series, if I want to identify these values, you can identify your series here. K is going from 0 to infinity of AR to the K is going to be, if I factor out an A, that is the value, that is my A value. 1 plus, then there is my R squared, R cubed, etc. The key to this is I have to have my A value and my R value, and that's where this is coming from. All right? It'll make more sense as we get into this. So let's do an example. So here's our first one. I'm going to scoot this up. Evaluate the geometric series or state that it diverges. Okay, so I have my geometric series going from 0 to infinity of 1.1 to the k. Now, what is my base here? 1.1. That's my r, right? It's ar to the k. R is the base of my exponent. So in this instance, r is now equal to 1.1. Now, what do you see about that? Yes, automatically greater than 1. So then this diverges and you're finished. There's no other work to do. This one diverges and we're done with it. Okay. Let's look at part B here. I have my infinite series from 0 to infinity of e to the negative k. Now, what happens when you have a negative exponent? Yeah, so this can actually be written as going from 0 to infinity of 1 over e to the k, right? If you have that negative k exponent, and you just have a 1 in the numerator here, you can move that e to the denominator, right? And then that whole thing goes to the k. If this were just e as my r value, it would be out, right? 2.718, that's greater than 1. But it's not. It's 1 over e. So pay attention. You have to know your exponents. You have to know this math, this basic math number sense coming into this. Okay, so what is my r value then? 1 over e, which we know to be less than 1. So if that is less than 1, because it's that fraction, right, like a little over 1/2, then we have, a little under 1/2 because it's 2.718. Then we have my value here is going to be, so we have a over 1 minus r to be my value. And if there is nothing in front of this a, or in front of this 1 over e, what is your a? Big fat 1, right? So if I now have this, I know that that is a 1. So my a value here is going to be a 1. And my r value is 1 over e. Do you see that? So this is a times r to the k. So that's my a. That is my r. Then you just do work. If I have a complex fraction, I'm going to multiply everything by e over e because that's my common denominator. And I get e over e minus 1. And that is the value. I'm not going to try. I mean, you could plug that into your calculator. Otherwise, there's no other way to figure that out, right? I'm not doing that in my head. E is a non-terminating decimal. So that's just going to be my exact answer. All right, let's do another one. What if we have this little fella right here? I am going from 2 to infinity of 3 times negative 0.75 to the k. Now, I want to point something out to you right now. If I have this, my k value here starts at 2. On my other problems and in my definition, I'm starting at 0. This one started at 0. This one started at 0. Both of them started at 0. So when you switch that up now and I'm starting this at 2, that's how that's going to affect this. My a value is not just a 3. My a value makes that impact. Now look at here. Before we do any of that business, we have to determine my r value. So I want to look at the absolute value of r has to be less than 1. Well, the absolute value of negative 0.75 is less than 1, so we're good to go. Now I'm going to write the terms out of this one because I want you to see what's going down. I'm starting this at 2. So I have 3 times negative 0.75 squared plus 3 times negative 0.75 cubed plus 3 times negative 0.75 to the 4th. Negative 0.75 to the 5th plus more of that. If I'm looking at what's in common with all of these? There's a 3 in common with every term, so I can factor that out. What else? Yes, negative 0.75 squared is also in common. Do you see that? Here, you take out your smallest exponent. There's a 0.75 squared that I can take out of all of these. So if that's the case, my first term now is going to be 1 when you factor out this greatest common factor. I factored a 3 out here and 2 of my negative 0.75s. So now I'm just left with negative 0.75. The 3 goes, and I have negative 0.75 squared because I took out 2 from there. I'm going to take out 2 from this next one, and I have negative 0.75 cubed, etc. Do you see that? And this is my point. This is why I'm going to scoot back over here. This is why I wrote this part out. When you don't have a 0 here, if you have a 0 here, then it's super obvious what your A and your R are. But if you don't, whatever's in common, whatever you have that's in common, so that you get this 1 right here, and then that is your R value. So I have this in common, which tells me this is going to be my A value, and this is my R value. Do you see that? Now what do you see just happen? Here is this exponent of 2. What is this exponent? Right? You got this. So A is going to be my, this value up front is going to be part of your A. The question is, do I pull any of my base to also be part of that A? And if you're starting at something other than 0, the answer to that question is yes. You do have to pull some extra things out of there. Okay. Oops. Let's just go black. Who cares? It's so we have A over 1 minus R as the actual value. My A here is 3, and I'm going to write this as a fraction because they're easier to work with. So I've got negative 3/4 squared over 1 minus here, and I know my R value is at negative 3/4 because that's R. I don't have a calculator, so just working these out just makes that easier. So now I have 3 times 9/16 over 1 plus, because I'm adding this. I'm just going to do, so I'm not going to write that 1 plus. So look at what's happening here. If I add that, you get a common denominator. So 3 plus 4 will give me 7/4. Then I multiply by that reciprocal. So this is really 3 times 9/16 times 4 over 7. So 4 goes into 16 4 times. And now I'm left with 27 over 28, and that's my actual value. All right, so you just do a little math, just some of that basic math to work that out, and then you can come up with your answer. All right, geometric series. So this is broken into 2 parts. Your geometric series is your first one, And then here it is. So you just look at this pattern, AR to the K. Anytime you see a geometric, or anytime you see a series with this pattern of AR to the K, that is considered a geometric series. We are going to be doing the same thing in this like we did with our integrals. What are my patterns? How can I recognize a type of series? And then that is the approach you take. If you have this to this exponent, you are going to be thinking geometric series.